Today we're going to further our knowledge of AS integration by introducing integrals with limits on, which would look somewhat like this, and also look at how to find the area underneath a curve, something like this. In example 1, we are asked to find this. Based on the last video, we know it's an integral because it's got this squiggly line and the dx, but this time we might say that we are integrating from -1 to 2, so from the bottom limit to the top limit. It probably makes more sense graphically, which we'll see later on, but for now we'll answer this question and we'll get a numerical answer. Previously, our answers have been in terms of x with a plus c at the end. This time the answer is going to be a number. Luckily, we don't need to change the process. We know how to integrate by adding 1 to the power and then dividing by that power, and that does not change here. The plus c is important when you're doing indefinite integrals, so when there are no limits, but in this case, we're not going to use a plus c. Instead, we'll put these square brackets around it, and we'll copy the limits -1 to 2. In order to find the value of this integral, what we do is we sub in the limits. We first start with subbing in the top limit, and then we subtract whatever we get when we sub in the bottom limit, like this. So 3/2 lots of 2 squared, subtract 3/2 lots of -1 squared, top limit, take away bottom. In this case, we are going to get 6 minus 3/2, which is 9/2. That's the answer, that's the full value of the integral of 3x from -1 to 2. Now for example 2, we follow the same process. Because it's an integral, we're going to integrate, and because there are 2 terms, we're going to integrate one at a time. So for the first one, we'll add 1 to the power to get 3 and divide by 3, divide by that power. For the 1, remember that any constant is the same constant with an x added on, the reasoning we saw in the last video, because x to the power of 0 becomes x to the power of 1 when integrated. Because it's got the limits, we're not going to put the plus c, rather we are going to put the brackets, the square brackets, with the numbers -2 and 0, copying the limits given in the question. Then we're going to substitute in the top limit for all of the x's, so 0 cubed over 3 minus 0. I would recommend putting this in brackets before you do the subtraction because there's going to be multiple negatives, and that's a common source of errors. We're going to subtract, we're now going to substitute -2 in for x, so -2 cubed over 3 minus -2, plenty of brackets. This will be simply 0. 0 times 0 is 0, minus 0 is still 0, but this term will give us something. We're going to have -8 over 3 plus 2, which is the same as 8 over 3 minus 2, which is the same as 2 over 3. So the integral from -2 to 0 of x squared minus 1 with respect to x is 2 over 3. Here are 2 for you to try. I'll give you a few seconds, pause now, have a go, and I'll give the answers in a moment. The answer to the first one should be 25 over 2. The answer to the second one should be 0. Okay, we finally get to find the area underneath a curve now. In this question, we're asked to find the area underneath the curve y equals x plus 2, which is there in green, the coordinate axes, so here and here, and then the line x equals 3, which is dotted. In this case, it's a trapezium, so we could absolutely find the area in another way, but I'll just show you that the integral works as well. So the area of the trapezium is going to be using the formula half a plus b h. A and B are going to be the height here and here, so that's going to be 2 plus this height is going to be 5, because when x is 3, 3 plus 2 is 5. That's the value of y over there. And then the height of this trapezium will be 3, even though it's on its side. So this will give 7 times 3, 21 over 2. Okay, that's what we could have done normally. That's what we could have done at GCSE level. What we're going to do now is we're going to find the integral from 0 to 3 of the curve x plus 2. No, it's not very curvy. And what we should see is that we'll get the same answer. Let's integrate it. We're going to get x squared over 2 plus 2x. Hopefully that process is becoming a bit more familiar now, with the limit being 0 and 3. And then what we're going to do is we're going to sub 3 in. So we're going to get 3 squared over 2 plus 2 lots of 3. And then we're going to subtract the lower limit. In this case, the lower limit is just going to be 0. Don't assume it's always going to be 0. 0 squared is 0. 2 times 0 is 0. But there are certain questions, certainly in second year, where the limit might be 0, but the answer won't be. So just keep an eye out for it. Putting that all together then, we're going to get 9 over 2 plus 6, which is, drum roll please, 21 over 2. So we get the same answer whether we do it using the area of the trapezium or when we do it this integral way. So why did we bother doing such a simple example that we could have done without using integration? Well, because this example we cannot do by using areas. If you remember back to GCSE, you might think, oh, well, we can count the squares. But that's not going to give us an exact answer. It's only going to be an estimate. With integration, we're going to be able to find the exact area of the region without any doubt. So to find this area, we're going to do an integral. We're going to be integrating the curve that we see there, x squared plus 1, and it's going to be with respect to x. The limits are going to be where this shape starts, which is over here on the axis, when x is 0, and it's going to end over here when the dotted line starts, which is at x equals 1. We're going to follow the usual process. We're going to integrate by adding 1 to the power and dividing like this. Put it in our square brackets and copy and paste the same limits. We're then going to sub the 1 in here as x and then the 0 in. So 1 cubed over 3 plus 1. And then we're going to subtract 0 cubed over 3 plus 0. Which, yes, is 0, but I'll write it down anyway. This gives us our final answer of 4 over 3. Now, by guessing or by counting squares, you would never be able to say it's exactly 4 over 3. So this is the power of integration. It tells us exactly what that area is going to be, right down to the very last decimal place. Over to you then. Time for an exercise. Could you find the area that's shaded between the curve that's called y, that's given as an equation there, the x-axis here, and the two lines x equals -1 and x equals 3. And if you can find the exact area rather than guessing or with squares, using integration, that will be what I'm looking for. Hopefully that's been enough time to try it. You've had time to pause. The answer I'm looking for is 44 over 3. Hopefully you got that. If not, try and go back through your working and see if you can come up with that answer. This next bit's neither an example nor an exercise, but it's just a bit of a warning. Something that may help you out in certain questions when your answer maybe doesn't seem right. So an integral, whatever an integral could be, it literally could be anything, the answer could be negative. It is possible that this value is negative. It is possible that the integral is positive. It is possible that the integral is 0. We saw one of the answers as 0 in the exercises before. However, if you're looking for the areas, then remember that areas are always positive. It doesn't make sense for an area to be negative. So in certain questions, if you might need to find the area of something like this, find this area here, then the integral that you find to help you work out the area will be negative. But what you have to do is you have to flip that into the positive realm, because area being positive is the only thing that makes sense. And similarly, if you've got some diagram like this, and you need to find the total area here to here, we have to do them separately, because one of them is going to be positive when we integrate it, and one of them is going to be negative. So we can't put those two integrals together. So if you ever see a question that's got two parts, one above the x-axis, one below, separate them out, do two integrals. One's going to be positive, which is just the area, exactly the same number. One's going to be negative, which you'd have to make positive when you're talking about the area before you can add the two together. Just something to watch out for. Hope that makes sense. Okay, time for a slightly harder example now. We're looking to find the area R again, but this time you'll notice that it's not completely underneath the curve. There's an extra line involved, which is cutting off part of it. What you've got to see in a case like this is that if you could find the integral underneath the curve, which is going to be the integral of 3x squared minus 2x plus 3, between the limits, starting at 0 again and going up to here, which is x coordinate of 1, this would give you this whole region here, which is underneath the curve and above the x-axis. But we don't want this triangle. So what we've got to do is try and find this area as well in yellow and subtract it. And as soon as we've subtracted it, we're left with the golden region R that we're looking for. So let's find the integral. That's going to be part of it in a question if you couldn't quite work out how to find the triangle or what shape to add on or take away. Finding the integral is going to get you at least some of the marks. So as usual, add 1 to the power. This time if we divide by 3, it disappears. Add 1 to the x to get x squared. Again, divide it by 2, it disappears, that coefficient. And then we're going to add on 3x. And we're going to do this between 0 and 1. When we do this between 0 and 1, the 0 is going to cancel out. And the 1 will give us 1 minus 1 plus 3, which is 3. So the total area, the total green bit is 3, the area underneath the curve. The area of the triangle is going to be half base times height. The height we can see there is 4. The base we can see is 1, is the coordinates. So the area of the triangle is going to be half of 1 times 4, which is 2. So what does that tell us about the area of R? It tells us it's going to be the green region, 3, subtract the triangle yellow region, 2, 3 minus 2, gives us our final answer of 1. This sort of question can be more complicated. My suggestion would be, if you can find where the two curves cross and draw straight down, that should help you find an area, maybe a triangle, maybe a square, maybe a trapezium, which you can take away or maybe add on certain questions to give you the region that you're looking for. And here's another exercise for you to try. This time I've broken it down a bit further because the question is a tiny bit harder. First of all, find the coordinates of the points A and B. And then once you've found those coordinates, use my hint about the vertical dotted lines down and try and find the area of the region R. In this case, you'll need a trapezium area and you'll need to do a subtraction. Good luck with it. Pause now and I'll give you the answer in a few seconds. The answer should be 32 over 3. Well done if you've got that. Well, there you have it. Now you know how to integrate any AS function with limits. Be sure to check out some exam style questions now to really solidify your understanding.